Hello. From this session, we will start to learn a few specific design methods for rock support in underground excavations. This session is on rock support design using Q rock mass classification system. Let us revisit the Q system. We have covered the learning of Q rock mass classification in the course of rock mechanics principles, session 4.2. You may want to go back to that session to refresh. I will only use the Q values for the design of the rock support. Here are the 6 parameters made up of Q value. We can obtain the values for each parameter from the Q table and then calculate the Q value. With the Q value, we will be able to classify the rock mass quality as shown in the table on the right. This is the first use of Q value to classify rock mass quality. The full name of the Q is Tunneling Quality Index. As the name suggests, the main purpose of Q is for tunnel design, specifically to assess rock tunnel quality, stability, and to design rock support for tunneling. Q system was developed as an empirical design of permanent tunnel support based on thousands of cases. Based on the Q system, tunnel stability is related to rock mass quality and opening size. Permanent support design also depends on tunnel safety requirements. Rock support can be designed using the Q design chart shown on the right. We just mentioned permanent support depends on tunnel safety requirements. Tunnels of different usage have different safety requirements. For example, railway tunnels require high safety compared to water transfer tunnels, understandably because human occupation in the railway tunnel. Safety requirement is measured by a term called excavation support ratio, ESR, which in turn gives the equivalent dimension, DE. Equivalent dimension is the actual excavation span or height divided by ESR. Now let us take a look at excavation support ratio. The table gives the ESR for different usage of tunnels. ESR is 1 for tunnels commonly used by human. That include tunnels for railway, for roads and highways, for underground power station caverns and the civil defense chambers, and for tunnel portals and intersections. Tunnels and caverns used by more people or more critical, such as railway stations, sports and public facilities, underground factories, and underground nuclear power station, are given the ESR of 0.8. For tunnels less used by people, then the ESR is greater than 1, with the type of the tunnels and the cabin usage, we can assign the ESR accordingly. For temporary opening, it has lower safety requirements and therefore is assigned higher ESR value. Now let us try with the Q support design chart. On the left, we have span or height of the tunnel and the ESR. At the base, we need Q value. Given the example that Q equal to 5, span equal to 60 meter, ESI is 0.8, we start from Q equal to 5 on the base axis, marked as 1. The next step is to find span over ESR, which is 16 over 0.8, gives 20 meter, marked as 2. With 20 meter on the left axis, we can find the intersection with Q of 5, and it is marked as 3. That intersection point 3 defines the support category, which is category 5. Fiber reinforced shotcrete, 5 to 9 cm, and the bolt. Since we have shotcrete, we will find bolt spacing in shotcreted area up as 4. It gives spacing 2.1 or 2.2 meters. Following 5, we can get bolt length, which is close to 5 meter. Note here, for finding bolt length here from the chart, we use the actual span of 16 meter. The steps summarized here are exactly what we did just now. Get Q on the base axis, get equivalent dimension on the left axis, find the intersection point and its support category. You're halfway there. Up from the intersection point to find the bolt spacing. On the right, you can find the bolt length using the actual span. Voila, it's done. For this particular example, the required roof support is to apply shotcrete of 7 to 8 centimeter thick and install systematic bolting of 5 meter long with a spacing of about 2.1 meter. Please take time to go through the last 2 slides and make sure you can find the support requirements. With the Q chart, let us examine a bit more in detail on the influence of ESR. We use the ESR on the left axis, which changes the location of intersection point up or down with the same Q value. This may change the support category. However, it does not change in the bolt spacing. Bolt length is determined by the actual span or height. It is not affected by ESR. Therefore, for support using bolts, the requirements on bolt length and spacing are not influenced by ESR. With the change of intersection point, if the change of support category is between category of the same kind, for example, 4 to 7, ESR effectively changes shotcrete thickness. When the change is crossing the category, say 3 to 4 or from 7 to 8, we were changing the support type. Within the support category of bolt and shotcrete, safety is improved by increasing shotcrete thickness. Effectively is protecting small blocks from falling. For lock support using systematic bolting, that is of category 3 to 7, bolt length and spacing can be estimated from the Q chart. Alternatively, they can also be estimated by the equations shown here. Bolt length in meter is equal to 1.4 plus 0.184 times the span in meter. Log of bolt spacing, again in meter, equals to 0.24 plus 0.12 log Q. This equation is suitable for bolt in shotcrete area. The common rock bolts are steel rebars with diameter of 20 to 24 millimeter. They have yield strength of about 175 to 250 kilonewton. On the other hand, spot bolting, indicated as category 2, is to secure individual rock blocks having potential instability problems. Clearly, we need to put bolts to where the potential unstable block and the wedges are. Therefore, there is no issue of bolt spacing, but to identify the exact locations of spot bolting. Potential unstable blocks and their dimensions can be estimated from the observations and analysis of joint spacing and joint orientation at the site. Bolt length should be sufficiently high to obtain adequate anchorage in the stable rocks beyond the bolted blocks. Typically, the bolt length should be at least 1 to 2 meters into the stable rocks behind the potential unstable block. That is, the block size plus 1 to 2 meters. You may also need to assess the block volume, particularly for larger blocks, to ensure that the bolt has sufficient strength to carry the block. From the Q chart, we are also able to estimate the maximum unsupported span. The triangular zone of lower right corner of the Q chart is the zone of unsupported stable zones for underground excavations in rocks. For good quality rock mass, it is possible to have the excavation unsupported for a long period. We can estimate the maximum unsupported span from the Q chart, or we can use the equation here, which is the equation of that red line. Maximum unsupported span in meter is 2 times ESR times Q to the power of 0.4. For example, if we have Q equal to 10, ESR equal to 1, the maximum unsupported span is therefore 5 meters. So far, we have gone through the rock support and the reinforcement design for roof support. As for most of the tunnels, caverns and mines are at shallow and medium depths, not exceeding 500 meters. the dominating failure is by gravity 4, particularly in competent yet joint rock mass. Roof, therefore, is the most likely to fail as compared to the side walls. We can, of course, using the Q chart to design rock reinforcements for sidewalls. Because sidewalls generally have lower risk of failure, we need to make some adjustment for the design. The suggested adjustments are for Q greater than 10, that is in generally good and very good rock mass, Q wall can be adjusted to be 5 times the original Q used for roof design. For Q between 0.1 and 10, rock mass quality of fair, poor, and very poor, Q wall adjust to 2.5 Q. For extremely and exceptionally poor rock mass quality, that is Q less than 0.1, the failure is no longer dominated by gravity and the joints. They are caused by high stress or squeezing, and therefore wall suffers the same potential failure as roof. Then Q wall is taken as Q. The ESI is the same, still need to be considered as it depends on the usage and the human occupation. As we mentioned in the last session, there's also the need for temporary support during excavation. It is to ensure the safe zone for the excavation and therefore is short-term. Temporary support measures are primarily bolts and shotcrete. For poor rock mass, steel sets are used. As temporary support does not require long-term safety, the following adjustments are suggested for the design using the Q chart. One is to increase QSR to 1.5 ESR or to increase Q to 5Q. I want to finish this session by going through a couple of examples of rock reinforcement and support design for underground excavations. Here is the first one. You are asked to design roof and wall reinforcements of a rock cavern to be used as a railway station. The cavern roof is 60 meters wide, the wall is 6 meters high, and the Q is 5. With railway station, ESR is 0.8, and the wall adjustment is Q wall equal to 2.5 Q. The support design obtained from the Q chart are shown here. The steps to obtain those supports are shown on the next slide. Ready to go to design the support using the Q chart? Let's start with the roof. Step 1, 2, 3, 4, and 5. We have the roof support in category 5 with a fiber reinforced concrete of 8 cm, systematic rock bolts at a spacing 2.2 meter and the length of 4.5 meter. Then the wall. With the adjusted Q wall, again, we can design the support for the roof, for the wall. Step 1, 2, 3, 4, and 5. You get a support design. It's category 3, both spacing at 2.4 meter, both lengths of 2.5 meter, and no shotcrete. You got it? Well done. Here is an example of what have been designed for underground excavation project in granitic rock mass. The excavations involved caverns of 30 meter span, main tunnels of 50 meter span, and other tunnels of 10 meter span. The whole underground development encountered rock mass from very poor to very good quality as shown by the Q values in the first column. Rock reinforcement designed for the roof of those tunnels and caverns at different rock mass qualities are shown in the table. Their reinforcements are bolts and shotcrete. Bolt length and spacing are shown in meters, and the shotcrete thickness are in millimeters. You may have noticed that for a given Q value, say 4 to 10 in third row, the designed bolt spacing is the same for tunnels of different span, all at 2.2 meter. Also, for a specific tunnel span, say 50 meter in the middle, the bolt length is the same for all rock mass quality at 4 meter length. Again, you should study the Q chart and understand the connection between support requirements, rock mass quality, and excavation dimension. I'm ending the session with some comments on using the Q system for rock reinforcement and support design in underground excavations. The Q system is perhaps best for competent rocks with rock mass quality of poor and above. That is, Q is higher than 1. For support categories 2 and 3, a thin layer of shotcrete at the roof is highest recommended. As we mentioned in the last session, shotcrete is extremely effective in stabilizing the excavation surface and the small rock blocks and the wedges that often cannot be bolted at wide spacing. For excavation of a very large span of more than 20 meters, in situ horizontal stress perpendicular to tunnel access should be taken into the design consideration. The favorable stress condition can effectively create a self-support stress arch over the roof. In the next session, we will learn how to use IMR to design rock support. Goodbye now and see you later.